quick recap of what we did in the last class. So, we were talking about the n path principle, and the basic idea, as we saw the last time around, was that we take an LPTV system. It is time varying at a frequency Fs, and for argument's sake, let us say I am going to just show one resistor which is varying with time, but in general they can have multiple conductances inside which are all varying with time with the same frequency, of course. And let us assume that this R of t is varying in some fashion, say like this. And this, of course, is T s, right. So, this is R of t, and if we excite the system somehow with an input e to the j 2 pi f t, as we saw yesterday, the output will simply be something of the form sigma over k, sum over k h sub k of j 2 pi f times e to the j 2 pi f plus k f s times t. Now, what we said was that if we took n such systems, right. Yesterday we looked at the example where n was 3, and here the time variation was shifted by by 3, R into t minus 2 T s by 3. And this basically, as we saw, would result in an LPTV system if we put all of this inside a box. And on the face of it, this also is an LPTV system, and since every component inside is varying at the rate f s, this is also an LPTV system which is varying at f s. But given the special nature of the three building blocks inside, as we saw yesterday, this can be written as h sub l, I mean sum over all l of 3 sub l h sub 3 l of j 2 pi f e to the j 2 pi f plus 3 l f s times t, all right. And we saw why this comes about. Yesterday we saw the whole this thing in the frequency domain. Today I will give you the intuition behind this in the time domain, as well as show you an example of the use of this n path principle. So, remember, when we talked about LPTV system, we said that in the time domain, remember h of t comma tau represents in an LPTV system the response at time t due to input applied at tau before the point of observation, which namely at t minus tau. All right. And what happens in a periodically time varying system? This is true for any linear time varying system. So, for any LPTV system, recall that h of t comma tau is the same as h of t plus Ts comma tau, right. So, in other words, if you move the time of observation and the time at which the impulse response the impulse is applied by the same Ts, then you will get the same response. Now, let us take this composite system. I am going to just for visualization show them in different colors. Red, blue and green. Sorry. Okay. So, this is some resistor R of t, this is R of t minus Ts by 3, this is R of t minus 2 Ts by 3. So, as if we looked at any just one of these systems in isolation, then clearly you basically, as you can see, for each of these systems in isolation, the impulse response will be periodic with time Ts, because each one but because this system is periodic at Ts, it is LPTV with Fs, right. Now, if I if I apply an impulse at delta of t minus tau, I am sorry, I apply an impulse at t minus tau. So, that basically means the input is delta of t minus tau, and I observe the output at t, then what will I get here? I will get h of t comma tau, correct. Now, if I take a snapshot of this system exactly at Ts by 3 later, all right. So, what happens? Right, let me copy, paste. Okay. So, I will now if I observe the output at time t plus Ts by 3, right, and what would happen with regard to the input, and if I apply the input at t minus tau plus Ts by 3. So, here the input is applied at t minus tau, correct. Here the input is applied at t minus tau plus Ts by 3. In other words, I have moved the input by Ts by 3, I have moved the output, the time of observation also to output observed at t plus Ts by 3, right. So, let us call this OP1 and we call this OP2, all right. So, if you move t, I mean remember R of t was like this, and what happens with R of t minus Ts by 3? Well, that does something like this. And R of t minus 2 Ts by 3, all right. Now, at time t, let us say this was some time at some observation time, is equal to t, right, for some particular observation time, that is that's the time I choose to look at. And what do we, how does the system look like? There is one of these boxes operating with a resistor of that value, one of these boxes operating with a resistor of that value, right, and the third box is operating at with that resistance value, correct. Okay. Now, let us see what happens if you go, and as a result you have some output at time t which is OP1, correct. So, now what comment can we make when we take the time of observation to be t plus Ts by 3 . This is time is t plus Ts by 3, right, and the output we are observing is OP2, that corresponds to this guy here, correct. So, it is the same system which has been excited at a time with an impulse at time t plus Ts by 3, right. So, so for example, in the first system you would have excited, let us call this let us call this, let us call, let us say we excited the system here, this was tau, correct. And so, the corresponding excitation in the second system will have to come here, that is T s by 3. It is delayed by T s by 3. The time of observation is also delayed by T s by 3, correct. So, think about this way. So, in the picture to the left, we excited the system here, where there was one the blue box had this value of resistance, the red box had this value of resistance, and the green box had this value of resistance. Now, at if we excited the system after T s by 3, well, there is the green box has that value of resistance, the blue box has this value of resistance. I think my diagram drawing is not really as good as it should be, but okay, and the red box has this value of resistance, correct. So, whatever output you would have got in with the blue box, right, when you applied the impulse at t minus tau, you would get that same output, right, with the green box in when you applied it at t minus tau plus t by 3, right. So, whatever, in other words, whatever output you were getting here, right, when you applied the input at t minus tau, you will now be getting this at what time now, in the green box. So, you will be getting this through that box, correct. Whatever output you were getting through the red box in the first case, you will now get through the blue box, right, and whatever you were getting through the green box before, right, you will get through the red box. And since all these three systems are identical, right, it does not matter, you know. So, in either case, basically the bottom line is that yeah, if you add the three up, the final output is going to be the same, right. So, output 1 at so H, the output is going to be H of let us call this so output 1 is going to be the same as output 2, right. So, if you think of the impulse response of this composite system as H hat of t comma tau, right. This is after all a LPTV system in its own right, all right, and so therefore, the output of the system at t is simply H hat of t comma tau, all right, and you will see that just because of what we have seen, the output of the system when looked at a time T s by 3 later is the same if the impulse was delayed by T s by 3 and the output was observed T s by 3 later, you would get the same output in both cases, right. So, H hat of t plus T s by 3 comma tau is the same as H hat of t comma tau. And what is this therefore saying? Yeah. So, this is saying that this composite system, the 3-path system, is LPTV at the rate 3fs, right, even though each system is only varying with a rate at fs. All right. In other words, another way of thinking about this is that if you take a photograph of the system, right, at a certain time, all right, the network looks exactly the same at a time Ts by 3 later, Ts by 3 later, and that happens because the 3 subsystems are exactly identical, but it is only the timing which is changed, right. If you take a snapshot or photograph of this system Ts by 3 later, what the red would have done, right, would be done by as we saw in this case, the green box will basically behave like the red box, and the blue box will behave like the green box, and so on, right. So, this is the time domain intuition behind n-path operation. So, one way of quickly recognizing whether the LPTV system is periodic at n times the frequency is to simply look at how the network is at a time Ts over n later, and apart from simply moving the components around, if the network actually looks the same, then you know that it is LPTV at Ts over n. Okay.